Okay. So we left off yesterday with the ratio test. And so remember that what do we have? We just have any series. And we compute the limit of the ratio of consecutive terms. So the absolute value of the ratio of consecutive terms. And then we just have if L is less than 1. So L is always going to be bigger or equal to 0 since we're taking absolute values. Series converges. L equals 1, inconclusive. And L bigger than 1 diverges. So note ratio test works well when higher order growth sequences appear. So we have our outline of order of growth of functions, natural log, we've got fractional, we've got polynomial growth, then we've got exponential growth, maybe to the n, excuse me. And then we've got factorial growth, and then beyond. So if you see anything that is geometric growth or beyond geometric growth, factorial growth, or n to the n type growth, ratio tests are good for these guys. For lower order, ratio test doesn't work that well. For polynomial, it often gives an inconclusive result. So let's take a look at a few examples. So with all of these, let's just try to figure out converge or diverge. So we'll start with the sum of, let's check these now. So let's compare something like an exponential relative to a factorial. So I've introduced this concept before and kind of mentioned how as we jump from an entire order of functions, an entire class of functions to the next, the rate of growth is significantly bigger. Meaning, of course, if it's in the denominator, the rate of decay of the overall function will be significantly faster as well. It will decrease to 0 really fast. And so we've seen before of why this limit of individual terms goes to 0. So it passes the divergence test. I know that the factorial will grow fast enough and will dominate the upper one, will dominate the geometric series. But now the question is it dominated fast enough so that the series itself converges? The sequence of individual terms will go to 0, but now we have this extra added metric of adding up all of the terms. And can we add up all the terms is what we're trying to discover. So anytime you see anything like this, No matter how they appear or where they appear in the series, you kind of always want to base your methods based on the strongest order of growth. So if you see a factorial or you see a geometric series, ratio test is always a good thing to start with to see if that'll work. So let's go ahead and do that. So we want to compute our limit of the ratio of consecutive terms. So again, good practice in showing your work, writing out, what the n plus first term is. This can be a little tricky for students when you guys first start to manipulate the algebra of sequences, especially with factorials in there. Sometimes it can be a little weird. So it's the quantity n plus 1 factorial. And then we want to compute the ratio of those two in absolute value. So we've got an plus 1 over an is going to be b to the n plus 1 over n plus 1 quantity factorial over b to the n, just n factorial here. I also recommend being very clear about your notation with your parentheses and your division signs, especially with the ratio tests, since we often have fractions as the sequence, irrational expressions as the sequence, then we're going to have sort of these compound fractions. So always be clear where the big dividing sign is. This is our next term. This was our previous term. And of course, we want to compute the limit now as n goes to infinity. And now when we do that, just got to mind all your algebra. So we will have bn plus 1 over n plus 1 factorial times n factorial over bn. Now, always group similar terms. So I put the factorials over each other. I put the exponentials over each other. And so here what we get b times n factorial over n plus 1 factorial. You got to mind your factorial algebra. And those divide. And now when we compute the limit as n goes to infinity of, well, we've got b over n plus 1 remaining, we just get 0. So by the ratio test, it converges, and it actually converges absolutely. We haven't introduced this yet. I'll mention what absolute convergence is here in a minute. It has to do with alternating sequences. But let's do one more example with these ratio tests.
I just had a quick question about this example.
Yeah.
So starting off, b was raised to an exponent of n, and then we got down to b over n plus 1. As the limit as n goes to infinity, if b is not raised to an exponent, it would not get iterated or increased as well.
No, right. So we do have b raised to the n. So if b wasn't raised to the n, if it was just a constant, we wouldn't have an n plus 1 or anything there. Was that your question?
Yeah, I just got a little confused on a lot of stuff.
Yeah. Okay, so let's try one more. Let's just give it a new page. And let's put some higher order growth stuff. Let's do something that has a little bit of everything. Let's see. What do we want to do? Let's do something like 2 to the n squared. Let's have 2n factorial. Let's say divided by n cubed times, let's say 2n to the n. Kind of put in a little bit of everything, and you know what? Let's make it alternating. So we've seen alternating series before. We'll actually see what happens, or we've seen alternating sequences before. We'll see what happens in specific cases with alternating sequences or series. But for the ratio tests, since we're taking absolute values, it isn't going to matter whether it's alternating or not. Really what we're trying to measure is the rate of growth. So we've got a lot going on. I have an exponential part, but within that exponential is a polynomial. It's not just 2 to the n, it's 2 to the n squared. So that's a little different. Now the exponent of the exponential function is increasing itself at a quadratic rate. We even have a factorial in the numerator, but in the denominator, we've got a polynomial times something like n to the n. And actually, maybe we'll change that. Let's just change this to n to the n. So what's going to happen with this guy? In some sense, well, we have this polynomial order of growth, but if we wanted to, we could simplify this. So 1 to the infinity, we've got a minus 1 to the n. We've got 2 to the n squared. We've got a 2n factorial. Denominator n to the n times n cubed is actually just going to give me n to the n plus 3 if we wanted to simplify that. Actually, a reason why I got rid of the 2, because it would just be a 2 to the n, which we could then simplify as well. So sometimes there's some simplifications you can do, especially with different orders of functions. But really now what we want to ask is, well, we have something that grows exponentially and fairly rapidly. It grows beyond exponentially because of the n squared in the exponential. We've got a factorial in the numerator as well. But then we have something like n to the n in the denominator. So will this decay fast enough? Will it pass the ratio test? Let's find out. So our an is given as written. I'll just keep that there. Let's write our an plus 1. We're going to have a minus 1 to the n plus 1. 2. So mind your parentheses with all these. N plus 1 factorial, or n plus 1 squared. And then the factorial will be 2 times the quantity n plus 1 factorial. Right? We are sticking in n plus 1 for all the n's and put those in a parentheses. Then we have n plus 1 raised to the n plus 1 plus 3. And so our...
Can you go back up for a sec?
Sorry. Yep. And so our ratio, an plus 1 over an, nicely enough, when we take the absolute value, The minus ones, not going to matter. We're going to have a minus 1 to the n plus 1, 2 to the n plus 1 squared times 2n plus 2 factorial divided by n plus 1 to the n plus 4 all over minus 1 to the n, 2 to the n squared, 2n factorial over n to the n plus 3. So those are our ratios. We're computing the limit. And so let's go ahead and write it out as, so the minus 1 and that minus 1, they're going to divide and give us a factor of minus 1. But when I take the absolute value, it's going to make everything positive. So I'm going to ignore the alternating part. And it's common practice to do that whenever you're computing these. You can essentially leave off the minus 1 to the n's because they're not going to make a difference in the ratio test. So let's go ahead and write it out as 2 to the n plus 1 squared, 2n plus 2 factorial divided by n plus 1 to the n plus 4 times, we will have n to the n plus 3 divided by 2 to the n squared and then 2n factorial. So all I did was take the reciprocal of the denominator here. And now we've got to do the algebraic skills to simplify this. So again, to do it in steps, to be careful, let's put everything that is similar over itself. I've got 2 to the n plus 1 squared and a 2 to the n squared. Those are our geometric parts, our exponential parts. The factorials, I'm going to line up. And then we've got the n to the n parts, n to the n plus 3 over n plus 1 to the n plus 4. So now I can simplify term by term. So this one might be a little tricky. So let's see what happens. We want to simplify this guy. Unfortunately, as it's written, simplification isn't going to be apparent. So let's do some scratch work over here. 2 to the n plus 1 squared is going to be 2 to the n squared plus 2n plus 1. So when we compute the ratio, the n squareds are going to cancel, and we're just going to be left with 2 to the 2n plus 1. From this term. Our factorials, we will have 2 to the n plus 2 times 2 to the n plus 1 times 2 to the n factorial, which will divide out that 2 to the n factorial. So again, our scratch work. So 2n plus 2, 2n plus 1 times 2n factorial is that numerator, of course, divided by 2n factorial. Those two will cancel. And now we've got to deal with this guy. So we've got times n to the n plus 3 over n plus 1 to the n plus 4. Let's get some more space here. Everyone caught up writing?
1 second, please. Okay, yeah, you're good.
Okay, so let's rewrite this. And let's see if we can get a conclusion out of this. So I wanted to throw everything in one example to kind of show you guys how a lot of this algebra is going to work. The ratio test, as we kind of saw, it works well with geometric series because the simplification ends up being pretty nice. Same thing with factorials. These n to the n terms are going to be tricky to work with. And these n to the n terms, the root test, which will be the next test we learn, is almost better, but the problem is the root test doesn't work well. The algebra isn't nice with all of the other terms. So let's see. How do we want to simplify that? That is n to the n. And this is n plus 1 to the n plus 4. So we can write this as limit as n goes to infinity of 2 to the n plus 1 times 2 to the n plus 2 to the n plus 1. Let's peel off these extra terms. So we have n to the n divided by n plus 1 to the n. Times, we have an n cubed over n plus 1 to the 4th. And so now we've got to do some fancy comparison tricks here. So far, all of these limits that we've been computing are all equal. And what I want to try to do is really focus on the highest order of growth and sort of ignore these constants. What's going to happen as n goes to infinity of these guys? Well, that's going to go to 0. I'm trying to think of the best way to explain it. We can bound it and essentially just kind of ignore those guys and then focus on this term. But the algebra and the math for this is going to get hairy. So I'm not sure if we have the tools to really compute the rest. The other thing I want to look at is the overall polynomial part. So these are now polynomial parts that we're essentially peeling off of these guys. And we have some polynomials here too. So this is going to be something that grows of like n squared. And we have an n cubed divided by an n to the 4th. Let's see, is there an easy way to do this?
couldn't you use a table to reason through it to prove that the bottom will get bigger than the top, which would prove that's convergent, or can you not do that?
Nah, you can't use tables. You got to use more analytical tools. So here's what we can do. Let's kind of combine our polynomial parts. You don't want to use tables. You can use tables to get an intuition for yourself, but tables aren't proofs. And so if you do tabular work and then kind of claim that as a proof of decreasing, that's not a Calc 2 skill. That's a pre-calc reasoning. And by Calc 2, to show that it's decreasing or something like that, you really got to use calc skills. So we've got 2n plus 1. And then this term is going to be, let's go ahead and multiply it out. We will have 4n squared. We've got 2n plus 4n plus 5n plus 3 times n cubed all over n plus 1 to the 4th times n to the n over n plus 1 to the n. And when we multiply that out, we'll have 4n to the 5th plus 5n to the 4th plus 3n cubed. The denominator, let's see. So some things we can do to manipulate this. Here I have something like n to the 5th. So I'm going to borrow another term here, n plus 1 to the 5th times, I'm going to pull out a 2. So it's a 2 times, here, let's pull out, if we pull out one factor of 2, this is going to be 2 to the n, or 2n quantity to the n, over n plus 1, now to the n minus 1. So we're getting a little closer. So why did I do these steps? One, I kind of like having the polynomials on the same order of growth, because now I can compute the limit of this term. And that's just going to be 4, since they are both 5th degree polynomials. And then this term we've got to keep working with a little bit. So we've got the limit as n goes to infinity of this guy times, so let's actually write it as 2 times, let's pull out one more factor of 2n. So we can write it like this. Everyone with me? And so now we have to figure out what this limit is. So let's go ahead and write it as, we can take this limit and get 4 times the limit as n goes to infinity of 4n times this guy. And how do we manipulate this guy? This guy is going to end up being a little wonky. So it's going to be 2 divided by 1 plus 1 over n to the n minus 1. And so now, what's going to happen with these terms? So we've got to remember all of our pre-calc skills that are coming in. We're going to have 4 times the limit as n goes to infinity of, we've got a 4n times, this is going to be, it might actually be better to split the exponents again. We've got a 2 to the n minus 1 over one plus 1 over n to the n minus 1. And I claim that this should go to infinity. So why is this going to go to infinity? Well, what's happening in the numerator? We've got a 4n and a 4n and a 2 to the n minus 1. In the denominator, we really have a 1 plus 1 over n to the n minus 1. Again, we can manipulate these terms to have it something like this. So now our denominator is going to go to infinity times the limit as n goes to infinity with this term is just going to be 1. And then now the denominator is going to go to a constant e. So since we have these 4n and 2 to the n minus 1s in the numerator, our limit overall is going to infinity. Questions on that one? So that one got a little tricky. I kind of just threw in a bunch of stuff. The n to the n's were the difficult ones. So factorials and exponentials worked really nicely with the ratio test, but it's these n to the n's and these combinations of factorials and or the quadratics and the exponents, which made things a little more tricky as well.
I have a question.
Yeah.
Are you allowed to do like different tests for sequences? Because like the components are to the power of n. Couldn't you have done the n test or the root test to cancel out the power of n and then analyze it from there?
So the root test, you got to just be careful of what tests you're doing, right? Because we have convergence of sequences and then convergence of series. So the ratio test and the root test are for convergence of series. And then once we set up those tests for the series, well, we've reduced the problem down to computing limits of sequences. So here we're computing the limit of the ratio of consecutive terms. And when we compute the ratio of consecutive terms, we're essentially creating a new sequence that we now have to analyze what's happening at infinity. So from that sequence, now we can use sequence tests for convergence. But the sequence tests that we know for convergence are mostly algebraic tools.
Oh, okay.
Did I miss a factor somewhere? I think someone mentioned it in the comments. It might have wrote it down wrong. So 2 to the 2n plus 1. And then when I go here, I did forget a factor of 2, didn't I? So that should be 2n plus 1 with all of these. And then so that's going to affect some of these numbers. It doesn't change the conclusion. Let's trace through and correct all of our algebraic mistakes. And this will be good practice for you guys. It is common to make small little errors like that. Then unfortunately they propagate through. So what was going on with this 2? Well, I wrote this as, it should be 2 to the 2n. And so here I have 2 to the 2n plus 1. I pulled out one factor of 2. And so what we have is 2 to the 2n times n to the n when I peel off that one factor. So this term isn't quite right. 2 to the 2n is going to be 4 to the n times n to the n. So 2 to the 2 to the n is another way how we could write that and get 4 to the n, which means now when I combine these two under 1n, this term here should have been a 4. So still the same conclusion. What's going to happen? We'll still have that power of 2. This guy will be a 4. Here, I'll make my marks in red too so you guys can see them. So that should have been a 4. That should have been a 4. Which means this guy should have been a 4. This guy should have been a 4. And this term should have been a 4. But luckily, that small little mistake of missing that 2 didn't affect our conclusion. Limits are still going to go to infinity. Other questions? Let's take a look at the root test real quick. So ratio test is going to be very good for exponentials, for factorials. It even works for those n to the n's, as we saw, but the n to the n terms, if they appear, you got to do a little bit more work, as we had that we're first into doing there, into factoring them out and peeling them off and trying to really compute a limit. So just kind of to reiterate some of the tricks I was using to work with these n to the n terms is you can always sort of factor off any finite number of them. So n to the n plus 3, I can write as n to the n times n cubed to kind of match up polynomial parts that I needed. And then likewise, once I was able to write the n to the n over n plus 1 to the n, and write those under one exponential, you can simplify this by factoring out a 1 over n. And nicely enough, when you have something like a 1 plus 1 over n raised to the n, hopefully we know and love that limit as well, in recognizing it as some sort of exponential, as e, I guess I should say. With the root test, let's go over that real quick, and then let's finish up with alternating series and then jump into more examples. I promise the examples won't be that hard. Most of the examples and most of the limits you'll have to compute only involve 1 or 2 different types of sequences. There I kind of threw in everything. We had polynomials, factorials, exponentials, and the n to the n's. So the root test says if we have a sequence or a series, and we compute the limit as n goes to infinity of the nth root of terms. And it's going to be L. Then just like the ratio test, if L is less than 1, the series converges. If L is equal to 1, inconclusive. And if L is bigger than 1, the series diverges. So note, this one works well with compositions under exponents. So, for example, let's say I want to do a series of 2n plus 1 over 3n minus 2. We know how to do that one. But now let's say I raise all of that to the n. So in other words, we have like a linear or a rational expression now composed with an exponential function. So what we can do then is to compute the limit as n goes to infinity of the nth root of the individual terms of our sequence. So in other words, if we have a sequence that looks geometric, something raised to the n, but that something is now some function, then this root test is going to work very well. And why is that? Well, of course, the nth roots are going to cancel each other out. And then when I compute this limit, we're going to get 2/3. 2/3 is less than 1. So by the root test, the series converges. Any questions on that? Do you guys want to see another example of those guys? Okay.
So
Oh, sorry. Go ahead.
I was gonna say, like, is this the only time, like, the only time you can use this test is usually if it's like to the power of n?
Pretty much. So
Okay.
we can try another example. So let's take a look, something similar to what we were just taking a look at, except maybe not as complicated, so we don't have to spend as much time on it. But what's going to happen if we have something like n factorial over now n to the n? Our intuition should tell us that this n to the n grows a lot faster than even factorials. So our problem, though, is just square roots in general, hopefully you've gathered, are kind of difficult to work with, let alone nth roots. So we have n factorial over n to the n, and we want to take the nth root of it. So the other way you can write it is, of course, to the power of 1 over n. But how's the algebra on this work out? It works nicely in the denominator. But what's going on in the numerator? The numerator have got a factorial. And they have a factorial raised to the 1 over n. So what is that limit? And we don't know. So unfortunately, this is kind of one of the problems with factorials, is that we would like to use some sort of L'Hopital's rule trick maybe with this, but since we don't have a L'Hopital's rule for factorials are a discrete function. They're not a function we can use for continuous functions at this level. So I don't know what this limit is. It's going to be a infinity to the 0. And we don't have a tool for really working with that. I mean, we could try to take a natural log, but then I've got a natural log of n factorial, and then how do we work with that? It gets a little complicated. I guess we could try to work it out if you guys want. So I don't think you'll have to do this, but for the sake, what we're considering is this limit as n goes to infinity of n factorial over 1 over n, which is going to give us an infinity to the 0, which is an indeterminate form. And so if we just call it, if we try to use some of our Calc 1 techniques, let's just call the limit L potentially infinite. And if I take a natural log of both sides, since natural log is continuous, we can bring the limit outside. And now how do we work with this guy? Natural log of n factorial is natural log of n plus natural log of n plus 1, n minus 1, excuse me, plus natural log of n minus 2. Because of the properties of factorials, it's n times n minus 1, and by our properties of natural logs, of splitting a product into a sum of natural logs, we can write something like this. And now, what's going to happen with this guy? Well, natural log of n over n is going to go to 0. Natural log of n minus 1 over n, each of these terms, if we write it, natural log of n over n plus natural log n minus 1 over n. When I compute this limit as n goes to infinity, all of those terms are 0. Which means the original limit we did is 1. So in other words, from that piece, when we were computing this limit, we showed that the numerator goes to 1 and the denominator is infinity, so that it goes to 0. So overall, the root test worked for this, but again, you gotta really know your algebra and understand how to break things down. Any questions? All right, let's take a break there. I'll let you guys degas a little bit. Take a look at some of those notes that I just threw a ton of crap at you. These are the skills involved. Some of these problems are a bit harder than a lot of the ones, at least that I'm looking at in terms of the book problems and the WebAssign problems and your homework problems. But a lot of them are just harder in the sense that I kind of just crammed a bunch of different examples together so that we could see how the different algebraic techniques work out for factorials, for exponentials, for the various types of functions. So the key thing with the previous two examples is to try to understand how each piece works, especially in the ratio test, and then a little bit in the root test. We'll take a look at the alternating series tests when we come back from break. Those are a bit easier as long as you were fine with the error bounds, with finding error bounds from integrals and integral approximations. These ones shouldn't be too bad. Okay, so we've only got a few minutes, 20 minutes or so. Let's go ahead and finish up with our alternating series test. The alternating series test is easy though. It actually makes things very nice. So alternating series test. Says, so suppose we have a sequence that satisfies this condition. This is a very nice and concise math condition. What are we saying with this condition? Both that all the terms of the sequence are bigger than 0. So it's a positive sequence, and bn plus 1 is less than bn, meaning that it's a decreasing. So it's decreasing and positive. Then if I make an alternating series out of it, it converges. Nothing more to it. So, example. This sequence, or the series, diverges. We've shown that the harmonic series doesn't converge, but so if we call our sequence an, then of course an plus 1 is going to be less than an. So it is monotonically decreasing. As n gets bigger, the overall sequence gets smaller. So it is a decreasing sequence. So if we see an alternating harmonic series, this converges by the alternating series test. So our terminology so for a series, be careful with just the notation and how we're introducing our terms. Sometimes we introduce a series and then peel the alternating part outside of that series. Sometimes we just say we have a sequence and create a series, and this could be an alternating series or it might not be an alternating series. could be either. It's just a generic sequence that we're creating a series out of. So for a general series, if the absolute value of Bn, if we take the absolute value of individual terms, so if this one converges, we say the series converges absolutely. If the series converges, but the absolute series diverges, we say the series converges conditionally. So this was the strength of the ratio test and the root test. If we get a positive test from the ratio test or the root test, it converges absolutely. Alternating series are kind of like it's a weaker sense of convergence, that it will only converge because some of the terms are positive, some of the terms are negative. And when some are positive, some are negative, they kind of cancel each other out, which helps the series converge. So in some sense, we can have a weaker rate of decay, something like 1 over n. We know that 1 over n diverges if I just try to add up all of those values. But if it's alternating, if some of the terms are positive, some of the terms are negative, then it will end up converges. So in other words, convergence for the alternating harmonic series will be conditionally convergent. The condition being that we need the alternating. So with those guys, I mean, a lot of the examples are pretty quick. Let's see. Like some of the book examples, whenever you see an alternating series, as long as you can show that the terms are decreasing. So we've got -1 to the n over square root of n cubed plus 2. So we see the alternating. We just have to show decreasing. If the problem just asks for convergence or divergence, this is all we have to do. So we consider just our sequence of terms without the alternating part. And then what we want to do, so let's call these guys, let's call them A sub n, is show that it's decreasing. And so there's a couple of ways to do that. We can either directly show that an plus 1 is less than an, which might be difficult, or we could model it with a function. And show that the function is strictly decreasing on the domain of our series. So we can show f of x is decreasing. On 1 to infinity. And that is just Calc 1. Sorry, not the cube root, square root of x cubed. Bottom derivative of the top minus the top, derivative of the bottom. It's going to be a mess. Let's give myself some more space here. So we've got the bottom. Let's use fractional exponents. Derivative of the top is 1 minus the top, derivative of the bottom. All over the bottom squared. And now we got to simplify that mess. And we do have a difference in the numerator, which makes things a little bit of a pain. So what we're going to do is factor out x cubed plus 2 to the minus 1/2. So that's going to be x cubed plus 2 to the 1/2 in the denominator. That'll make that x cubed plus 2 minus 1/2 x times 3x squared. And then overall, let's see, 3/2 x squared. That's going to give me a minus 1/2 x cubed. Plus 2 over x cubed plus 2 to the 3/2. And how do we do our number line test? So we only care from 1 to infinity. Pick a number bigger than 1. What's going to happen? Actually, I don't like that because it's going to have a 0 at the cube root of 4. So, not entirely great. Let's say we pick something bigger than 2. 2 cubed is 8. Minus 1/2 will give us -4 plus 2. Give us a negative number. In the denominator, it'll always be positive. Well, positive if I plug in positive values. So overall, it'll be a negative over a positive, which is negative over here. In between 1 and 2, actually wonky stuff for this function is gonna be going on. So f of x is actually not decreasing on 1 to infinity, but it is eventually decreasing. So f of x is decreasing on at least 2 to infinity is what we showed. So from 2 to infinity, I know that this is decreasing, or at least, sorry, this piece is decreasing. So by our alternating series test, it converges. And of course, this is finite. So overall, it will converge. Last thing we got to touch on, sorry, we only have a few minutes to cover this, is the alternating series. remainder theorem. So recall that we have a sequence of partial sums. And let's keep the alternating part off. I don't think it's a big deal, but we'll just keep it like that. And then let's call S the full sum. Then, so suppose it converges. We have a convergent alternating series. Then the error, if I only add up a finite number of terms, in other words, I'm looking at the difference between the total sum minus the partial sum, it's always going to be less than or equal to the next term in the sequence. So just as we did with error bounds for integrals, anytime they give you the error bound or they say find the sum accurate within 3 decimal places or accurate within a certain margin of error, this is the formula we want to use. So example, find the sum and they give us the margin of error to be something like 0.0001. So all we know is that the margin of error, it's always going to be less than or equal to the absolute value of the n plus first term. And then since we want that to be less than 0.0001, we just put the 0.001. If we can make the n plus first term less than that, then I know that the error will be less than that. And this will tell us how many terms we need to add up. So it might ask, find the number of terms or find, add the sequence or compute the sequence up to this degree of error, in which case first we need to find the number of terms and then add them up. Or it might just straight up ask how many terms do we need to add up to be within this margin of error. So our bn plus 1 absolute value is easy enough, so we can get rid of the alternating part. And what we're trying to solve now is just 1 over n plus 1 times 5 to the n plus 1 is less than or equal to 1 over 10,000. And so we will get 10,000 less than or equal to n plus 1 times 5 to the n plus 1. And unfortunately, with a lot of these problems, especially the ones on WebAssign and the ones from the book, we can't really solve for n here. A lot of it's guess and check. What is n going to be? Like 5, maybe? So this is the type of one where you can use a calculator. Use a calculator or make a table, of n plus 1 times 5 to the n. Certainly with n equals 3, we'll have something like 5 to the 4th, which is 625 times 4, which isn't going to be high enough. So it's going to be something like probably 5 or 6 should give it to us. Always make sure to round up. right? Because we need this expression to be strictly bigger than 10,000. And n has to be an integer. Any questions on that?
Couldn't you split up the 5 and then divide 5 to the other side? So then you only have to do n plus 1 times 5 to the power of n?
Yeah, if you want to. That's a good little manipulation you saw there. Good. Sounds like you guys are catching up on some of these algebraic techniques, or at least your algebraic techniques from pre-calc. Manipulating exponents is still good. So we've got a 5 to the n. If we divide both sides by 5, as Ryan was saying, 10,000 over 5 is 2,000. N plus 1, 5 to the n. Sure. Whatever helps you compute it. And again, if you want to kind of make a table and just do kind of like, you know, n and then bn, or at least compute n plus 1 times 5 to the n. Go through. I'm guessing it should be about 5 or 6. Should be enough. Other questions? Okay, so we are out of time today. I would love to do a lot more examples with you guys. I had a bunch written down, but there's just a million examples that we can do and a million different techniques we can throw at you with these. Hopefully, at least with the 2 problems we kind of saw, I kind of just crammed all of the techniques into one problem, especially with the ratio tests and root tests. Now your practice and your problem is to look at series in general and throw in all of these different techniques, when to use the ratio test, when to look for a limit comparison, or use the alternating series to break things down. So come to office hours tonight. I imagine office hours will be a big problem solving seminar in some sense. So 2 to 4, and then hopefully we'll get you guys squared away with homeworks and you won't have too much to do over this weekend, because it is a long weekend and I do think everyone deserves a break. This is the middle of the semester. It's been a hard semester. It's been a fast semester. 3-day weekend would be nice for everyone. So I'd love to help you guys get caught up and not have too much to do so you can enjoy the weekend.